All right, so let's continue. I wrote again the formulas for the Fourier-Bessel coefficients involving the type of boundary conditions we had in this problem, and let's start from where we left it in the previous part. So we established that the solution should be of this form, and how do we find basically these coefficients yet to be determined? We just plug in this format of the solution everywhere in the non-homogeneous problem, and then we're going to aim. That's another crucial step. Remember, we have to write the non-homogeneous term and the non-homogeneous boundary condition in terms of the same type of Fourier-Bessel series. So that's the key thing, right? Otherwise you won't be able to find matching of the coefficients. So we need Q naught, and think of Q naught as basically equal to 1, right? I mean, you could basically look at a series for 1, but we'll leave it as a constant. So we need Q naught and A rho squared as Fourier-Bessel series of the same type. You will see that for Q naught stuff, that part is actually easier. In fact, again, because Q naught is a constant, you can actually take 1 as a function and write it as a Fourier-Bessel series. So that will be trivial, and let me illustrate why that's the case. Because just like the cosine series, I mean, if you think about hard enough, you realize that you can think of 1 as 1 plus 0, 0, 0, 0. But even if you don't realize that it has a trivial Bessel series, you just apply the formula, and this integral won't be that difficult to compute. So let's say again that f of x is equal to 1. Well, we're going to use rho basically, right? Because now we're going to switch to rho instead of x when we use these formulas. So if f of rho equals 1, then a1 following this formula, that's going to be 2 over 1 squared, because remember the radius is 1 in my case. Rho, f of rho is a constant, 1 d rho. So that's going to be 2 antiderivative rho squared over 2 between 0 and 1, and 2 cancels, and therefore a1 is equal to 1 again for the function equal to 1. The rest of the coefficients, aj, so aj will be the following the formula over here, 2 over 1 squared, so that's going to be 2 over j naught of alpha j squared, again because c is equal to 1. The integral from 0 to 1 rho times 1, which is the function itself, j naught alpha j rho d rho. Just for practice, remember the next step is always the same when you deal with these problems. Make the substitution s equal alpha j rho, ds equal alpha j d rho, j naught of alpha j squared on the outside. The new bounds are 0 and alpha j. And then here we have, let's see, s over alpha j, j naught of s, and then d rho is ds over alpha j. Let's do one more step here. We pull out 2 over j squared of alpha j, another alpha j squared on the outside, and you're left with sj naught. And remember, the antiderivative of sj naught is sj1. So sj1 of s between 0 and alpha j. But this is equal to 0 minus 0 because remember, always remember where alpha j come from, right? So I mean, if I plug in alpha j into j1, that's the boundary condition, which basically led to where alpha j come from, and in this case, it comes from j naught prime, which is the same as j1. So whenever you plug in alpha j into j1, you get 0. And then when you plug in 0 for s, of course, it's 0 minus 0. So 1 has a trivial Fourier-Bessel series. So we're going to have 1 equals 1 plus summation from 2 to infinity, 0 times j naught of alpha j rho. I write it like that because technically this is 1 plus 0 plus 0 dot dot dot, because I want you to see basically how you identify the coefficients when you plug it in into the actual problem. And then of course we're going to have a formula for c squared, for x rho squared, and in my case again look at the formula for x squared in the previous part, but the same type of Fourier series for rho squared when c equals 1 will be 1 over 2 plus summation from 2 to infinity 4 over alpha j squared j naught of alpha j naught of alpha j rho. Make sure you pause and catch up if you need to, to look at these terms and the previous notes that are not here right now on this page. Okay, so let's now plug in finally into the non-homogeneous problem, all that kind of stuff, and then see how we can end up with the equations for a1 of t, aj of t. And that's going to be the last part that I'm going to go over, and you finish the problem after that. So look at the series format of the solution. Okay, so we're going to plug it in. Let me put it here one more time. So we're going to plug in this part, this summation into the PDE. So keep in mind on the left side we're going to do partial t of everything here, so that won't affect rho. On the right hand side we're going to do partial rho in this expression. You see partial rho twice, 1 over rho partial rho. So a1 of t will disappear on the right hand side because it's by itself. So partial rho of this guy will be 0, and we will only differentiate basically j naught of alpha j rho in this expression here, because aj of t will be pulled out as a factor. This will be a constant with respect to rho. So aj of t won't be affected. Maybe you can take a moment and plug it in yourself and then check with me. But what we end up with is the following. So on the left side, we're going to have a1 prime of t. Let's see it like that. So a1 prime of t plus summation from 2 to infinity a j prime of t j naught of alpha j rho. On the right hand side will be, because a1 of t goes away, right? So you will have summation from 2 to infinity aj of t, and j naught of alpha j rho comes into that expression u partial rho twice, so it will be j naught of alpha j rho double prime. I'm going to use the prime notation because this one depends on rho only, right? So partial rho twice, that's double prime, plus 1 over rho, and then j naught of alpha j rho prime. And then instead of q naught, I'm going to write it here, it's going to be q naught times 1 in the form of the series we developed earlier, right, on the previous page. 1 plus summation from 2 to infinity 0 j naught of alpha j rho. All right, so there will be one more little trick in order to identify the coefficients, but let me make another comparison with what we dealt with in the case of sine and cosine Fourier series. So the idea was to identify the coefficients of each type of eigenfunction. So cosine of nx, identify with whatever is multiplied by cosine of nx. The stuff outside of the summation, identified left and right, and that will give you an ODE for a1 of t. The problem here is that you need to basically write this part in terms of j naught of alpha j rho, because we can't do the identification in that form if you look carefully, right? I mean, here I have something times j naught of alpha j rho. This is alpha j rho, j naught of alpha j rho, but this part here, we have to actually take these derivatives and try to write the whole thing in terms of j naught of alpha j rho. So this is the little trick that if you remember, you save a lot of time, because if you remember where this comes from, you can replace it immediately with what you should basically replace with. So that's the reason if you go back to the beginning of our discussion, in the first page, if you remember, I said that keep in mind that J naught of alpha J rho solves the Bessel equation of order 0. So this quantity that appears in the summation, J naught double prime plus 1 over rho J naught prime, is nothing but minus alpha squared J naught, right? So again, this expression which appears in the summation is minus alpha squared J naught of alpha rho, which means in my case, this guy here is nothing but minus alpha J squared J naught of alpha J rho. So I'm going to rewrite the whole thing. And we have aj of t, and here, like I said, this whole thing is nothing but minus alpha j squared J naught of alpha J rho plus, let's actually multiply by q naught times 1 plus summation q times 0 is still 0, summation from 2 to infinity 0 J naught of alpha J rho. All right, so the last hurdle before we write down the differential equations corresponding to A1 and AJ of t, we need to plug in the Fourier-Bessel series for the initial condition, right? So u of rho 0, which was given to be a rho squared. Now, again, plug in the series format of the solution, so that will be summation, it'll be a1 of 0 plus summation from 2 to infinity a j of 0 J naught alpha J rho should be a rho squared, but instead of rho squared, of course, plug in the same format, the corresponding series for rho squared. So if you go back to, let's see where I wrote that. I wrote again on the first page. This is the moment when you need this, again, when c equals 1. So I'm going to replace rho squared with this whole stuff in terms of rho, and then c equals 1. So that'll be 1 over 2 plus summation from 2 to infinity 4 over alpha j squared J naught of alpha j, like I see is 1 again, J naught of alpha j rho. All right, so what are the ODEs to solve? So the last step, again, which is your job from now on. Okay, well, let's identify the terms outside the summation. So look carefully. A1 prime of t must be equal to Q naught. That's it. Okay, everything else is in the summation, right? So from 2 to infinity, you identify the coefficients of J naught of alpha j. A1 of 0, it's the constant, again, outside the summation for the initial condition. So one ODE to solve will be A1 prime of t equals Q naught with the initial condition A1 of 0 equals A over 2. And then the ODE for AJ came from matching the coefficients of J naught. So AJ prime of t will be minus alpha j squared AJ of t plus 0. I put plus 0 just to understand that normally you take this into account as well, because in some other problems it won't be 0, right? And the initial condition AJ naught of 0 comes from, let's not forget A, right? So the coefficient of J naught is 4A over alpha j squared J naught of alpha j. All right, so again, take your time, go over the problem one more time, and it might be useful to go back to the method of variation of parameters and see how we dealt with those problems. And you will, as a good sign that you understood the topic, the process should look familiar to you. So I mean, when you look at the problems, the one involving sine and cosine series and what I just did should lead you to the conclusion that, okay, it's kind of the same stuff, right? I find the eigenfunctions, I take a series solution with those eigenfunctions with coefficients in terms of t, plug that format everywhere in the non-homogeneous problem, and again, write everything in terms of the non-homogeneous term, the initial condition in terms of the same type of series. And if I do my job correctly and I don't make algebra mistakes, I'm going to end up with a nice initial value problem for each of those coefficients. So that'll be the end of this chapter. Just an overview of what happens after the exam. Hopefully we have enough time. If not, we'll adjust it. But it's more of the same thing, essentially, but involving a different type of Sturmoville problem. You will see that in the case of spherical coordinates, in some problems involving spherical coordinates, the Sturmoville problem is again a new one. And it's called the Legendre equation. So it's yet another second order ODE without solutions in the closed format. So solutions have to be obtained in a series format. And that leads again to another chapter of studying those types of solutions. So just like these Bessel functions were these weird solutions that came from the Bessel equation, the equation that comes out from spherical coordinates is called the Legendre equation. And understandably so, its solutions are called Legendre functions. So more on that, of course, after the exam. That's it for today.